So our opening keynote is going to be delivered by Dr. Montasir Qasymeh. He's Associate Provost at Abu Dhabi University. You might have seen him yesterday. He's going to talk about enabling the scalability of quantum microwave systems, which has traditionally relied on the use of large cryogenic dilution refrigerators, and share perspective on how that's changing and morphing. So please join me in welcoming Dr. Montasir.
Good morning. Thank you so much, Chris. Well, we're going to be talking about advancing connectivity at the microwave level. And of course, it's a very hot topic nowadays. If you're going to be looking into the market space of quantum technologies, despite everything that we have mentioned, despite all problems, despite, all the way that yet need to be done, we are talking about, I cannot see it from there, it's about $8,000 million by 2032. That's a lot of money. And if you're going to be looking into, for example, look at the quantum computing in healthcare, you find that more than half of that is based on superconductors. It's based on microwave superconductors. So if you're going to be doing a rough estimation, you're talking about $4 million by 32. That's a very significant market space, and this is the least, ladies and gentlemen. If you're going to be, if a breakthrough happens there, it will be a game changer, and maybe things will even very much be underestimated at this point. If you're going to be looking into how to scale quantum computers, hardware speaking, as a matter of fact, adding 1 qubit is costing about $10,000. So, from scientific point of view, if you need, for example, to reach into what's so-called the supremacy, the quantum supremacy, you're talking about a million qubits. That's $1 billion. So, ladies and gentlemen, it seems that there must be a solution for that. Just scaling the cryogenic refrigerator, economically speaking, at least, is very much challenging. Thus, that invite us to investigate how to connect cryogenic refrigerators over distance. We need to think about a distributed superconductor quantum computing. We need a simple, like let's say that this is the kind of the things that we are looking for. We need a simple implementation. And it seems so far that having, a refrigerator connecting these kind of, distributed cryostats are not solution. Because, I know some colleagues do that. What they do, they have a cryostat one, you have another refrigerator, they have a waveguide in between, and they just freeze it. It's just a third type of, cryostats. And you're still talking about the same amount of cost. So having that said, we were thinking first of all, we were thinking about transduction. They say, okay, fine, we have optical fibers, optical signals, even quantum optical signals are good for transmission. Superconductors are good for signal processing. So hey, let's just transform a microwave signal, quantum microwave signal, into an optical one, have it good for transmission, and then receive it at the receiver side, process it again to the microwave level, and so on and so forth. We started by looking at that, and of course there's challenges associated with it. We'll discuss it now. And then we end up with the technological challenges. The technique it was based on graphene layers. We'll discuss it right now briefly. That technique was not ready from technological point of view. Meaning to say, once we approached industry and we wanted to implement it, it was challenging from a technological point of view, but that technique inspired us to have, a graphene-based modulator that it could be used in classical and could be used in quantum domains as well. We would like to discuss it. However, the main theme of today is the third theme. We need to discuss how to connect two cryostat refrigerators by a typical waveguide, aluminum waveguide, that's not refrigerated, with no transduction. So we need to discuss it from the principal point of view. I quote here Dr. Ray yesterday. He said, engineering-wise, there is a lot of room. There is plenty of space for improvement, and this is true. We are, at least pitching for an engineering technique today. So starting by a microwave to optical conversion, indeed, it's a topic that has attracted the attention of many people since many years, and there are already many techniques there, reported, tested, characterized. These techniques, I'm talking about converting a microwave quantum signal into an optical quantum signal for the purpose of transmission. Doesn't matter for which utility, like coherent conversion from microwave signal into an optical signal. And the techniques that could be atomic interface techniques, it could be optomechanical techniques, and it could be electro-optical techniques. Among many, the electro-optical based techniques are with a wideband operation, are tunable, are scalable, they are integrable, you can put them in a chip if you advance the technology, so they seem very much promising. However, what we know, I'm an optical guy, I came from the optics. What we know is that lithium niobate, which is known as the best electro-optic materials, are indeed with a weak electro-optic coefficients. Mostly it needs a microvolt signal so that can be operated. So having a microwave quantum driving source for such a material for the purpose of conversion is challenging. What people do, they use resonators. So they have that crystal, lithium niobate, and put it in a resonator, and they do the conversion. That has consequences. That has some limitations. So what we did, we say, okay, fine. What are we going to be doing? We will propose this structure that you're looking at. This structure is a layered graphene. It's a periodic medium from optical point of view. It's a capacitor from electrical point of view. And what's special about this that you're looking at is that in quantum, ladies and gentlemen, once you have a laser and you have a driving microwave, let's say voltage, quantum one, you are talking about a microvolt level. You have an upper sideband and you have a lower sideband. The ones that I'm referring to, I don't know if I have a laser here. So here is it's not clear because it's green. Here is, the one, that frequency one, F1, is your classical pump. That classical pump is subjected to this layer, or you can even think of it as a lithium niobate, same structure. It generates upper sideband, a lower sideband. People used to say, maybe 15 years ago, that using this is no good because you might have a spontaneous emission. F1 is converted to F3 even without a microwave photon. And that incoherent conversion, right? But, thanks to this structure, it's a periodic from optical point of view. You can design it so that the lower sideband, F3, is suppressed by principle. It doesn't even, because how you generate F1 and F2 is a parametric operation. And by designing your, F3 is not clear here, apologies, by designing F3 to be at the resonance of the periodic structure so that it's suppressed by nature. So theoretically, we have a Gauss extraction ratio, so we have a coherent conversion, and the number of photons converted from microwave to optical seems good. So from scientific point of view, we're okay, and we said, okay, let's implement it now. Let's, approach industry. Let's build this kind of nice structure. Shouldn't be very much expensive, and let's see how things will go. And what happened at that point, we said, okay, let's look at the bigger image. It's not only conversion. This is an optical modulator. And the optical modulators, ladies and gentlemen, is a big market as well. You are talking about $30 billion by 2027. So what we are trying to do is these traditional lithium niobate modulators that you see to the corner can be replaced by a layered graphene. And those that you are looking at are in the centimeter, with a package, with a centimeter range, and they work only for a millivolt driving, unless you put it in a certain resonance, specific conditions. Ours, as a proposition, it's much smaller. It works, or it operates with a microvolt, and it is integrable. It's compatible with silicon. So you can be, you can afford extremely low driving microwave signal, which means quantum technologies. That's a $4 billion market size. You can have a compact structure, which means that you can have it in sensing technologies. That's a $7 billion. You can have an integrated, structure, so that you have, based on the silicon techniques and everything, this is another, $3 billion. So very much attractive. We have scientific publications, and we have, a patent according to that. When we came to implementation and approaching our, industry, we found that this is technologically challenging. The technology as of now cannot afford such a structure. You cannot, that's fine. The graphene fabrication is there. People can do, graphene for you, but have it like 1.5 micrometer connected this way is something difficult to do. I reached out to many people everywhere, but the promise is that one day the technology will get matured, and you're going to be able to produce this thing. So that brought us again to square zero with this question, ladies and gentlemen. If you are having Curiosat 1, where you have a quantum computer there, and Curiosat 2, where you have another quantum computer there, is it in principle possible to have a waveguide, aluminum waveguide, 3 centimeters by 2 centimeters, at room temperature connecting these two? So is that possible from engineering point of view? If you talk to principles, yeah, it's not possible, because at room temperature, 5 gigahertz, you are having about 1.2 thousand thermally generated photons. This is overwhelming, right? We cannot do that. So what we said, okay, fine, let's propose, ladies and gentlemen, this structure. And this structure, what you have there, you have a Curiosat 1, you have a source, you have an amplifier, what they call it, pre-amplification. And the trick is to design an antenna at the receiver side, where that antenna suppresses all signal, suppresses all received signals. That antenna that you see there with design dimensions, induce a voltage across the LC resonators from, or generated or inducted from the radiation, the propagating mode in the waveguide, just a typical waveguide with a typical propagating microwave mode. And what happened there, you can design the antenna dimensions to scale everything down. So if you are having 1,000, like what we see, 1,000 noise-generated photons, incoherent photons, they will be scaled down. And according to calculations, it's so easy to scale 1,000 thermally generated photons into a probability of less than 1. The number of photons is less than 1, so they are slim. But if you do that, you are also scaling your signal. The signal will be scaled down. Well, the trick is you have a pre-amplification there. The trick is to have a pre-amplification there. So the bit is that according to the commercially available devices, let's just use a commercially available parameters for a pre-amplifier G, cryogenic one, for a waveguide, aluminum waveguide, typical aluminum waveguide at room temperature, and for an antenna, it will be in the sub-millimeters dimensions, and for an antenna that's refrigerated as well. And let's develop a model for that. Unfortunately, I don't have the laser here. The B here, what you see there, is the operator generated at the receiver side, at the LC resonators over there. And the S you see there is the signal that's generated by the source. What kind of noise you need to take into account? First of all, the source itself has its own noise. Second, the amplifier is not an ideal amplifier. It has a noise figure. It generates noise as well. Third, the thermal generation in the waveguide. Fourth, the waveguide itself is loosey, so that the waveguide itself, according to attenuation fluctuation theory, adds a noise. All of them are taken into account. If you look into there, this is at the bottom. This is the number of photons received at the receiver side. The blue one is your signal, and the red one is all components of noise that we have talking about. And the trick is the coupling parameter, that in red, is something that we control, because it can be controlled by the antenna itself. If you're going to be looking into the input-output theory, or like taking the input-output theory and looking to the system, your system looks like that. And if you look at FW here, the operator, this operator with W, it's the noise one. It loads the two sides. It loads the receiver and it loads the transmitter. But we don't care about loading the transmitter because we can get rid of it. You just put a circulator there. It's still loading the receiver. So we agree at the receiver side you have different components of noise, but the most killing one, the most impacting one is the thermally generated F. So the bit now is that if we design our antenna, this is the antenna of the receiver, that we know how to design it so easy that kappa, that's coupling parameter, is something that we can control. The bit now, let's play with these parameters and put commercially, let's say real parameters, just take it from the data sheets and see how things go. The first thing that we have done, we calculated the system temperature, equivalent temperature. This concept, system equivalent temperature, is taken from satellite communications because satellite communication is very sensitive to these kind of things. It's subjected to the sun. So what happens is that they calculate the system temperatures as a parameter, or let's say as an indicator of how noisy is your system. The least system temperature you can get is the quantum limit noise temperature. If everything is refrigerated, with the best what we can do in this earth, you get the quantum noise temperature. If you compare your system temperature to that limit, it tells how good you are or how far you are from being perfect. And the table that you see there, the graph that you see there, it shows according to calculations, if you provide enough gain, you are really approaching the quantum limit noise temperature, meaning to say noise is really being suppressed to a good extent. This is for a 100-meter waveguide length, an aluminum one, and the gain, the preamplifier gain, is taken from an actual gain, an actual amplifier parameters with an actual, with all components, with the noise figure, with everything. If you would like to see the other way around, here is the gain at 40, which is the maximum what we can afford according to commercially available amplifiers, versus frequency, versus the waveguide length. And you can see, for example, if you take, the red, for example, or the blue is 5 gigahertz connectivity. Quantum computers works at 10 gigahertz usually, but it can be designed for any. If you look at the blue, you can see that, or take the red, which is 10. You can see that the system equivalent temperature could be as much as 10 times as the limit that you can get when you are freezing everything. And that could be up to 60 meters or up to 40 meters. That's a good indication. That tells you that, okay, fine, really noise can be limited. But how acceptable is that? How good is that? And the answer is, let's calculate the fidelity of a qubit. If you are having a qubit transmitted using this system and received at the receiver, how similar is the qubit at the receiver to the one at the transmitter? And that can be quantified by fidelity. And if you look into here, you find that for a 100-meter waveguide, the fidelity could be as good as 95% for even a 100 meter for like a high gain, for a 40 gigabit. And this is pretty much, let's say, promising, because if you move next, because look at that, at 40, let's fix the gain, because the gain is something that you can afford the best that you can, and let's see how far or how long could be the waveguide. It tells you, the calculations tells you, up to 100 meter, for a 10 gigahertz, you can afford more than 95% waveguide, 95% fidelity. This is very much, ladies and gentlemen, promising, because if you combine, such a fidelity with quantum error correction, the theory says, I know quantum error correction is another battle. People are fighting there, and we hope that people will do something, some progress soon, or in the near future. Quantum error correction combined with 95%, it can be reaching 99.99999. But if you remove everything I mentioned today, remove the amplifier, remove the antenna, put a typical waveguide, I did that calculations, and I found the fidelity 70%. Quantum error correction cannot help at the 70%. So what I'm saying is, combining the technique I'm trying to sell today with the promise of the quantum error correction, you can afford connecting cryostats with a waveguide that costs you $10 instead of $1 billion. You see that, and yet with an acceptable quality. Of course, I'm biased to my things. You need to pay for the preamplifier, which is costly a ton of bit, but it's of no comparison to a gigantic, to a large refrigerator that huge respected companies are paying for that. So this is my message. As a matter of fact, we are open for collaboration in the two aspects, for the graphene one and here, because we have done the calculations, the proof of concept, we have patented our technology, but yet we need to test it and we need to characterize it, because we know model is something and reality is a different thing. And maybe at some point when quantum error corrections is ready, we need to test it with the quantum error corrections. And that we hope to be a significant addition to the technology that we are talking about. So I would like to thank you so much, ladies and gentlemen, and I'm open to any question if there is any.